Okay, thanks, James, for the opportunity to speak. Thank you all for your attention and interest in my talk. I should mention that I'm recently affiliated with Clemson University, although the majority of this work was done while I was a graduate student at Washington University in St. Louis. So the plan is this. So first, we're going to talk about some background just to get on the same page and talk about the main motivating theorem. Then we're going to talk about two methods to prove this theorem. And then we're going to talk about some results that ideas motivated by these methods were used to get at. Okay, so the operators we're looking at are Calderon-Zygmund operators, which are a type of singular integral operator. So these operators are defined by integration against a kernel function, and that kernel function possesses some sort of singularity. So first, let's describe the kernel function. We have a function k that's defined on Rn cross Rn, but it's not defined on the diagonal. So we're not going to allow the two inputs to be equal to each other. So there's where the singularity is. But to compensate, it has to have some regularity properties that will save us. So the one property is the size estimate. So it has to have some decay. As you can see, you can't allow x and y to be the same because then you'll be dividing by 0 and the world will end. So it has a singularity on the diagonal, and also it just barely fails to be integrable when x and y are infinitely far away. So it just barely fails to be integrable at infinity. But with the second property, which looks kind of confusing as it's written, but you can imagine, like, say y and y prime are the same, so this term here won't appear. And if you divide the x minus x prime over, it looks like a difference quotient. So this is somehow describing the smoothness of your kernel function. And it's basically saying that if you take a derivative of your kernel, then it's going to decay like n plus 1 over this argument to the n plus delta power. So you gain a little bit of extra integrability at infinity when you take a derivative. This is the point. And then with these conditions, our operator is going to be defined by integration against that kernel. You take your input function f, you multiply by your kernel, and you integrate. And we're going to assume a priori that our operator is bounded on L2. Okay, so these are the operators that we're going to care about in this talk. And let's talk about a couple of examples that we might be familiar with. The first one is the Hilbert transform. So this is just defined by convolution with the kernel function 1 over x. So it has this form, and you can see easily that our kernel function is 1 over pi times 1 over x minus y, which satisfies the previous conditions in dimension n equals 1. So this is just defined on functions on the real line. And we're also going to talk about higher dimensional analogs of this. So if we're working Rn now and we just fix a value j that's between 1 and n, we can define the jth Riesz transform by this formula. So if we notice that if we take n equals 1, then this formula will collapse and it'll just give you the Hilbert transform. So we should think of this as a higher dimensional analog of the Hilbert transform. This is one that we're going to have to keep in mind, so we'll talk about this in more detail later. Okay, so a property about these Calderon-Zygmund operators that's important for many interpretations and applications of this theory is that they have a so-called strong type PP property, which just says that these operators are bounded from LP space to LP space. So just for some definitions, we're talking about these P integrable functions, and the norm is take it to the Pth power, integrate, and then to the 1 over P power. So all of these Calderon-Zygmund operators have this property, but we should ask, they have this property when the exponent P is in the open interval from 1 to infinity. So we should ask what happens, is this parenthesis necessary, or should this really be a bracket? What happens at these endpoints? In particular, what happens at the endpoint P equals 1? Well, we can see that in general, the inequality will fail when P equals 1, because we can take just the Hilbert transform, and if we apply the Hilbert transform to just a characteristic function of an interval, so it's just 1 when you're inside the interval and 0 otherwise, you can just integrate, and you'll see that the Hilbert transform is going to be this logarithm, and that function won't even be an L1. So it can't be bounded from L1 to itself. So this really should be a parenthesis and not a bracket. Now the question is, what can we say at this endpoint? Is there some other replacement property? And the thing we're going to do is, instead of saying it's going to be bounded from L1 into L1, we're going to make the target space larger, which will make the left-hand side of this inequality smaller, and therefore the inequality more likely to be true. And the way we do that is with this property, which is called the weak type 1,1 property. So it's not strong type 1,1, but it will be weak type 1,1, which says, instead of looking at the L1 space, we're looking at this weak L1 space, which is denoted by L1 comma infinity. The norm is given by this. And using this formula and a simple argument with Chebyshev's inequality, we can show that L1 is properly contained in this weak L1 space. So this quantity here is really smaller than the L1 norm. And this is actually going to be true. So this is the replacement property that we were thinking about for the failed L1 boundedness of Calderon-Zygmund operators. And this is really the main theorem that we're going to be discussing today. And actually, I should mention that the strong type PP properties on the previous slide actually follow from this property here in an interpolation argument. Okay, so how is this proved? The classical proof that kind of stems from the 50s uses what's now called the Calderon-Zygmund decomposition. So this is a decomposition of your input function f into good pieces and bad pieces, and it relies on a stopping time argument and maximal functions and averages of your function. But in particular, it relies on the doubling property of the Lebesgue measure that we're working with. So what is the doubling condition, this doubling property? So in general, if we have a Borel measure on a metric measure space, we say it's doubling if it has this condition, uniformly over all x and all r. So basically it says if you have a ball, of course, the reverse inequality of this is going to be true because it's a set containment. The ball of radius r is going to be contained inside the ball of radius 2r, but it's saying that these two quantities are comparable. You can kind of take a ball of a fixed dilation and shrink it back to your smaller ball that it contains. And those two quantities will be comparable. So I'm using this lesson or squiggle to say there might be an implicit constant here that will not depend on any parameters that we care about. So it's comparable up to some constant that we don't care about. So this is a doubling property. The Lebesgue measure has that. And what if we are working in a space where that property does not hold? Can we still have a consistent theory of Calderon-Zygmund operators? Can we still have this weak type 1,1 property? So in one setting that's been studied where we don't have the doubling property and we still want to study these Calderon-Zygmund operators is in a so-called non-homogeneous space. So let's say we have a metric measure space with a Borel measure mu, and instead of insisting that it satisfies the doubling condition, we're going to instead impose this different condition, this polynomial growth condition. So the measure of balls are going to grow like r to some power. So they're going to grow like radius to some power, but they don't necessarily have to be able to double back and be comparable to shrunken dilations of the original ball. Okay, and in this setting, in 98, Nazarov, Trail, and Volberg sort of reestablished the theory of Calderon-Zygmund operators in non-homogeneous spaces. And the theorem that we're interested in is if you have a non-homogeneous space and a Calderon-Zygmund operator, which is suitably defined on such a non-homogeneous space, it will still satisfy the weak 1,1 property. So I'm just basically changing RNs to X's and the Lebesgue measure to M's. And the theorem still holds. But the thing is, this setting doesn't have the doubling property, so therefore you don't have the Calderon-Zygmund decomposition, and this requires a different proof. So I want to describe both of these proofs. I want to describe the Calderon-Zygmund decomposition proof that's been known since the 50s or so, and I want to describe this more recent proof of Nazarov, Trail, and Volberg, which avoids doubling property. And just for notational simplicity, since the Lebesgue measure has this type of comparability that the balls in the Lebesgue measure are like r to the n, both of these proofs will apply in the setting of the Lebesgue measure. So I'm just going to describe both of these proofs in broad strokes in the setting of Rn with Lebesgue measure. Okay, so in that setting, what are we trying to do? We have an L1 function, we have a positive parameter lambda, that comes from the way that the weak L1 norm is actually defined. And we want to prove this inequality, where this implicit constant that's denoted in this squiggle does not depend on the f and does not depend on the lambda, but maybe it'll depend on the dimension of your space n, or maybe it'll depend on some parameters of your Calderon-Zygmund kernel k, but in particular does not depend on lambda or f. So we want to prove that inequality. So the first step is we're going to use the Calderon-Zygmund decomposition to decompose f into its to a good function and a bad function. So we use G for good and B for bad. G is good because it's actually going to be an L infinity function. It's going to be bounded. So that's a good property. B will not be bounded, but to compensate, we can further decompose it into an infinite sum of BJs, which will have other properties which will save us. So what am I talking about exactly? The properties of G are it's going to be an L infinity, and the L infinity norm is going to be bounded above by some constant we don't care about times lambda, and it's going to be controlled in L1 by F. These BJs, the pieces that sum together to give you the bad function B, are going to be supported on pairwise disjoint cubes, and the total measure of these cubes is going to be no worse than 1 over lambda times L1 of norm of F, which is good because that's exactly what we want to control everything by at the end of the day. The BJs also have this property that they have cancellation, so they integrate to 0, which will be useful. They have this useful L1 control by lambda times the measure of their support, and they're controlled in L1 by the L1 norm of F. Okay, so this, I know I'm just writing this on a slide, but if you want to prove it, it might take a page or two, and it uses maximal functions and studying averages and doubling property. In particular, for these 3 properties, you need to use the doubling property. So that's something to keep in mind when we discuss the second proof in a minute or so. But if you have your function f equals in this way, then the proof is not going to be so bad, because what we do is we can take our set that we're trying to, this quantity, this level set that we're trying to estimate, and we can split that up into studying the good function and the bad function. So this is just the accountable subadditivity and literal set inclusion. So the set is going to be contained in this set because f is equal to g plus b. And then with this bad function, we're going to need to work away from the support. So what we do is we take the supports of each bj, we're going to inflate them a little bit by some appropriate number. These inflations are okay because we have the doubling property. And then we're going to take the union of all of these inflations of cubes. So we're basically taking the support of b, inflating it a little bit, and defining that to be this omega star. And then for the next step, we're going to intersect this second term with omega star and its complement. So in particular, when we're analyzing this bad function, we only have to consider x's that are far enough away from the support of b. But with these 3 pieces, then we can finish the estimate, because with the good function, don't want to give all the details necessary because it'll take too much time. But what you do is you do a Chebyshev inequality with the power of 2. So then you're going to get an L2 norm of TG on the right-hand side. Then you can use the a priori boundedness of T on L2. Remember, we're assuming a priori that's bounded on L2. So then you're going to get an L2 norm of G. And then you can peel off an L infinity estimate on G. That was the first property that required the doubling property for G. And then use the fact that G and L1 is controlled by F and L1. So this is like a 4-line argument to get this inequality, which isn't so bad. This second part is because omega star is the union of these QJ stars, and each QJ star is basically a dilation of QJ. Using the doubling property, we can relate that to just the measure of each of the QJs. And then the second property on the previous slide said that the measure of the support of B, which would be the sum of the measures of the QJs, is no worse than this 1 over lambda times the L1 norm of F. So basically you take the set, use a doubling property to relate it to the QJs, and then the property that the support of B is no worse than 1 over lambda times the L1 norm of F. The last term is a little bit more complicated, but since we're away from this exceptional set, since we're away from this inflation of since we're away from the inflation of the support of B, we can do a Chebyshev inequality with power of 1. And then this basically allows us to use the smoothness estimate of the kernel. Remember, we said that if we take a derivative of the kernel, then we get this extra decay at infinity. Since x is in this region, that allows us to use that property, and that essentially lets us do an L1 estimate, which gets us what we want. So in each of these 3 terms, we get the quantity that we want, and that finishes the proof. And just to emphasize, we have to, again, use the doubling property for this term. Okay, so for the next proof, we want to avoid those red spots where we use the doubling property and still get the same estimate. So the proof has to differ already at the beginning. It's going to be somewhat similar in flavor, but it's going to have to be different. So the way that we decompose our functions is going to have to be different as well. So at the beginning, we're going to set this set omega to be just where f is larger than lambda. So we're looking at this level set of f. And if we assume f is nice enough, which we can always do by density, we can apply a Whitney decomposition because the set would be open. And we're going to decompose this into a bunch of cubes. So each qj is going to be a cube in Rn, where the distance from the cube to the complement of the set where it lives is comparable to its diameter. So basically you have a set, you're decomposing into a bunch of cubes, and when you're close to the boundary of that set, you're gonna have a bunch of small cubes. And if you're far away from the boundary of that set, you can have larger cubes. And then we can directly define the good functions and the bad functions by the good function is going to be f restricted to the complement of this level set. B is going to be f living inside of here. So it's just f where it's bigger than lambda. And we can decompose B into these BJs where we're restricting to each of these Whitney cubes. Okay, so it's more of a straightforward decomposition. And we can still get some nice properties of these. So in particular, we have the L infinity control of G, which is easy to see because we're on the complement of omega. So this inequality here goes the other direction. And there's no implicit constant here anymore. So it's less than or equal to lambda. And you have L1 control because of the restriction of F. We still have this property that the support of B is going to have good measure, meaning bounded above by 1 over lambda times the L1 norm of F. And that's just looking at this and using Chebyshev's inequality. And we still have this L1 control of B because, again, B is a restriction of F. But we don't have a couple of the other properties, meaning like we don't have the cancellation of the BJs. These functions BJ don't integrate to 0, which we'll have to get around that in a little bit. Okay, but with this decomposition, we can start the next step of the proof in the same way. We can split into t applied to the good function, t applied to the bad function, and we can intersect this term with the bad function with the set omega and the complement of the set omega. So this looks like a very similar setup. This part is going to be the same. You can still do an L2 estimate with Chebyshev, and then you can do the a priori boundedness of T on L2 and use the L infinity and L1 control of the good function G. So this term is going to be good for the exact same reasons as before. This term here is also going to be good because of the second property on the previous slide. This is just the level set where F is bigger than lambda. So you can do Chebyshev's inequality and you get exactly right to here in one step. And this one we have to work a little bit harder. Remember with the Calderon-Zygmund decomposition, we would do an L1 estimate with Chebyshev's inequality and then use the fact that the bad functions Bj integrate to 0. And that would allow us to use the smoothness condition on the kernel and get what we want. But the way we set things up, these Bjs do not have cancellation. So what we do, again, this term here is okay, this term here is okay. What we do is we add and subtract a measure nu that's going to force cancellation inside of the argument of this term. Okay, so we're going to take a set xj that's in each of these qj's. We're going to get these weights aj, which are just the integral of bj, which in this case are not necessarily 0. Well, not going to be 0. And we're going to define this linear combination of these weighted Dirac mass measures. We add and subtract t applied to that nu. And now this is engineered to have cancellation. So this term now we can control in exactly the same way as in the Calderon-Zygmund decomposition because each of these arguments will have mean value 0. And then we're left to control this term where t is applied to this linear combination of these weighted Dirac masses, which I'm going to leave as a claim. Really, that would take a few pages to prove. Just to say about some things that are involved in that proof, you have to again approximate each of these terms with these Dirac masses by some pairwise disjoint Borel sets. And then you're going to continue the estimate using the size condition of the kernel, the first property of the two properties of the kernel at the beginning. Then you'll use the polynomial growth condition of the measure, and you'll have to pass to the adjoint and use some Kotler lemma for a maximal truncation operator. But that's all just kind of technical stuff that I don't feel like talking about now for the sake of time. But the point of this proof is you can do a direct decomposition of your L1 function f and reduce to the case where you're applying T to a bunch of point masses. So you reduce to a bunch of point masses. That's the key of their proof. Okay, so now let's talk about some results of these ideas. And I want to remind you, this is a motivating theorem, just the classical weak 1-1 theorem in setting of a Lebesgue measure in Rn. And remember, the proof of Nazarov, Trail, and Volberg was in this non-homogeneous space where you don't have the doubling property. So a kind of natural question is, what happens if you actually allow the doubling property again and you try to run the same proof? Of course, it works at face value like we just saw, but are there any shortcuts we can make? And the first result I want to say is that if you run the same scheme, you can start with the same decomposition, but if you allow the doubling property, things can simplify quite drastically. So you can follow the general scheme of Nazarov, Chill, and Volberg and their argument, but you don't have to approximate by its point masses. So therefore, you won't need this size condition of the kernel. You don't need the polynomial growth condition. You don't need to pass to an adjoint. You don't need this Kotler lemma for the maximal truncated operator. So instead, what you do is you would just directly approximate the bad function as Bj by some constructed Borel sets. And then you can get a term that looks like the union of these Borel sets, and using the doubling property, you can bound this. So it's a different proof in this classical setting, which in my opinion is easier to understand because you don't have to deal with averages and stopping time arguments and all these things. Okay, so we can talk about this a little bit, but this is not really what I want to spend the most time on. But there's weighted versions of these where you change the measure. So let's say before we were having a Lebesgue measure, but let's look at more general, absolutely continuous measures. The natural type of ways to define this is we take a function f that is locally integrable, or sorry, a function w that is locally integrable, w standing for weight, and we're going to consider the measure w dx. So absolutely continuous given by w. And a natural class of weights that we look at in harmonic analysis are these Muckenhaupt AP classes. So if you have exponent p that's between 1 and infinity, 1 inclusive, then you can, and w is positive almost everywhere. If it satisfies this condition, we say it's an AP weight. It looks kind of complicated, but if you imagine that these averages, this 1 over q in the integral and this 1 over q in the integral weren't there, point-wise, these two things multiplied together are just always going to give you 1, right? Because this is the Holder exponent, and you can do some Holder exponent computations, and this whole thing is just going to give you 1. But this is saying that that identity is going to somehow hold in an averaging sense. So it's kind of saying it's like a fair weight. And these classify when maximal functions or when Riesz transforms are bounded on these weighted LP spaces. And when you're doing it for the case when p equals 1, and you're looking at the weak 1-1 inequality, that inequality can take multiple forms. So notice in this theorem down here, if the weight w is just equal to the constant function 1, all of this collapses to the classical weak 1-1 property on the previous slide. But if we allow these weights, let's say they're in an AP class for p bigger than or equal to 1, then we can get this theorem to hold true. So it's a little bit, it's more general when we're looking at absolutely continuous weights, and you can have this quantitative estimate. So this theorem here was proved originally by Ambrosi, Perez, and Recchi in 2016. Their proof is very similar to the original Calderon-Zygmund decomposition. And another result in this previous paper is proving the same theorem using this adapted Nazarov-Trail-Volberg idea. Okay, so let's talk about some more extensions of this theory. So if we were talking about linear Calderon-Zygmund operators before, so you had a Calderon-Zygmund kernel that took in 2 parameters, but now we're going to be talking about multilinear ones. So it's going to take in x and then a tuple, an m tuple of parameters y. It's going to have this size condition. And again, this is some complicated looking smoothness condition, but it's really saying that the derivative of this kernel is somehow possesses a little bit extra decay with an exponent of delta here. So yeah, if m is equal to 1, then this is going to be a linear Calderon-Zygmund kernel, and these conditions are going to look exactly like what was on the first slide. And our operator, again, is going to be defined in very similar of a way. If m is equal to 1, it's going to collapse to the same exact definition as the first slide again. But in this multilinear setting, things are a little bit more complicated. So we're going to assume that's a priori bounded from some LQ tuple to an LQ space that necessarily has to satisfy some holder condition. The correct target space is Q between 1 over M and infinity. Remember, if M is equal to 1, this is just going to be 1. And our operator is defined by integration against this kernel. Okay, in this setting, it doesn't have a weak type 1, 1 property, but it has a weak type 1, 1, 1, 1, 1, 1 into a target 1 over weak L1 over M space. So that inequality, by definition, will look like this. And this was known since 2002. It was originally proved by Perfakos and Torres. Their proof uses a Calderon-Zygmund decomposition. Since then, there were a few subsequent proofs. One was Maldonado and Nybo in 2009. They did this for a class of pseudo-differential operators, which actually includes these. Another proof in 2014 in the bilinear case was with Perez and Torres, which gave a simplified proof of what was going on here with a different type of smoothness condition. And then in 2019, Wick and myself gave a proof using this Nazarov-Schell-Volberg method. Okay, so 2 slides ago, we talked about a weighted weak 1, 1 inequality. Now we're talking about a multilinear weak type inequality. So you might guess that the next slide is talking about a multilinear weighted weak type inequality. So this is all technical, and but what this is saying is you, instead of having just a weight, an AP weight with 1, for the multilinear setting, we're going to have a tuple of weights, and they need to satisfy some conditions. And this is what the Muckenhout AP condition looks like in the multilinear setting. Again, if M is equal to 1, this will collapse to the ordinary AP condition for linear Calderon-Zygmund operators. And to make things quantitative, you can classify these multilinear AP weights by some conditions about this product weight VW being in a linear AP class, and each of these component weights, WIs, each of those being in a linear AP class. So you can go between the linear conditions and this multilinear condition, and there's some quantitative dependence if you trace through their proofs, and this is what that would look like. Okay. But if you want to if you want to combine both of these theorems, you can. And the theorem says if you have a multilinear Calderon-Zygmund operator and you have a tuple of weights that are in this A11 class, then you can get this mixed weighted weak type inequality for the multilinear Calderon-Zygmund operators. And in this paper, there's 2 proofs given. One is a weighted generalization of that Perez and Torres proof, and one is a generalization and actually a simplification of the proof that Brett and I gave in 2019. Okay, but I want to move on to 2 other applications that I think are probably more interesting now because they have more interesting open questions that I want to talk about. And one is with a limited range theorem. So let me kind of motivate this a little bit. And if we remember what we were talking about with the proofs towards the beginning, both of them, when you're dealing with a bad function, you had to do an L1 estimate that relied on the smoothness condition of your kernel. So the point is this whole weak type 1, 1 estimate is necessarily going to rely on the fact that your kernel K has some extra decay when you take a derivative. So it has to have some sort of smoothness hypothesis. So historically what happens, or here's the way we want to present it, is that this is going to rely on the smoothness estimate, and we're going to assume, just for some simplicity in the notation, that our kernel is actually of convolution type. So the K of x comma y is actually going to be a function of one variable, which the input is going to be x minus y. Typically what we could assume is that the gradient is just going to be controlled by 1 over x to the n plus first. This is the simplest way, and the most direct way we can present this. If we have one of these kernels of convolution type, then we can literally just say that the derivative has some extra decay at infinity. So this is sufficient for the weak type estimate and therefore the whole theory. But we can weaken this a little bit to get this Lipschitz condition, which is what was on the first slide, essentially. This is the convolution type formulation of that condition. And as we said since the first slide, that this condition here is going to be sufficient for the weak type property. And actually the gradient condition is going to imply this. but we can weaken this further and still get the weak type property. So this Lipschitz condition is actually going to apply this integral condition, which is known as the Hormander condition, which says that this difference here is going to be controlled when you integrate over this region of x's bigger than 2 times y, that this is going to be controlled in L infinity. So the natural question is, can we have another implication, another condition down here that will be weaker and still give you a substantial theory? So the question is, how far can the smoothest condition be weakened so that we can still get some interesting theory? So before I can tell you what that is, I need to tell you the definition for the next condition. So notice that this basically is an L infinity condition, right? You're taking a supremum over these y's, and this here, you're integrating the x variable. So this is a function of y. This integral here is a function of y, and you're saying that the L infinity norm of this function of y is finite. So keeping that in mind, that leads to this type of generalization. So we're going to say we have this LR adapted smoothness condition. So we're going to take a parameter R that's between 1 and infinity, and we're going to take a kernel that's defined away from the origin, so it possesses some sort of singularity. We're going to say it's in the class HR if this quantity here is finite. So remember from the previous slide, we're basically looking at what's inside of these parentheses. So an integral of this difference, and we were saying that that was an L infinity. So instead of saying that that's an L infinity, we're going to say that it's an LR with respect to this average over a ball uniformly over the size of these balls. Okay, so it's, instead of taking L infinity norms, we're taking LR norms of this quantity. So some remark is that this will coincide with the Hormander condition when R is equal to infinity, because it's, instead of doing an LR norm, we're doing an L infinity norm, which is exactly what was on the previous slide. And also these classes are going to become larger as the index becomes smaller. So the smallest case is when you have the Hormander condition, but as you decrease this exponent R, you're going to see pretty easier with Holder's inequality that these spaces are going to get larger. So this is a weaker condition formally than the Hormander condition for R's that are less than infinity. Okay, so we have basically a fourth condition that's weaker than all three in the previous slide. So what can we say if we assume this condition? So the theorem, which is now in the Bulletin of Hellenic Math Society of Grafakos and myself, is that if we assume that K is in this HQ prime, so this is the Holder conjugate exponent of our parameter Q. If we assume that K is in an HQ prime condition for the kernel, and we have an associated singular integral operator that's defined by integration against that kernel, and we assume that it's bounded on some LS space, and typically it's take S equals to 2, then it's going to possess a weak type QQ property. So it's not necessarily going to be weak type 1,1, but it's going to be weak type QQ for Q possibly bigger than 1. And there's two proofs in this paper. One follows the Calderon-Zygmund decomposition, one follows the Nasaroff, Chill, and Volberg type of ideas. But the point is, if we have a weak type QQ property, we can still use interpolation, and we can say that it's bounded on LP, a strong type PP property. It's going to be bounded on LP for P's that are in this range. And if Q is bigger than 1 and S is less than infinity, which in the way that we should be thinking about it, that would be the case, then this is going to be properly contained in the interval 1 to infinity. So using those three conditions that are typically assumed, you get a weak type 1,1 property, and therefore LP bounds for all P that are between 1 and infinity. Using this weakened condition, we're still going to get LP bounds, but it's going to be in a smaller interval. So let's just digest this in a special case. If we assume a priori that our operator T is bounded on L2, and we're going to take a kernel that's in the HQ prime, then our theorem says that T is going to be weak type QQ, and it's going to be bounded for all P in this Holder symmetric interval. So from this, we can assume a weaker smoothness condition and still get an interesting theory, but there's still some open questions here that we're trying to solve. So we're not sure if we don't have a proof of the fact that, or the question that is this interval Q to Q prime, is this the largest interval in 1 to infinity, where all these operators would extend to be bounded? Can we actually, the question is, can we take this limited range interval, Q to Q prime, and can we make that bigger, assuming the smoothest condition adapted to HQ prime. And a related question is the inclusion of these kernel conditions, right? We can prove this set containment pretty easily using Holder's inequality, but is this strict? Are there examples of kernels that satisfy the HR1 condition that would not satisfy the HR2 condition? And that's going to be related to this question here as well. So we don't know how to do that exactly. We're fishing around for examples of operators that have such a property. But if you're interested in thinking about this, I think that a place to start would be to consider Riesz transforms that are associated to differential operators of divergence form. There's, going across the literature, there's some examples of Koenig and papers of O'Shea that have Riesz transforms of this type that are proved to be bounded on some range of P's that are Holder symmetric and that are unbounded outside of that range. So the question is, could these operators possibly satisfy our condition? Don't know yet. Okay, I want to talk about one other question that actually we're working on over the summer with an RU group. We've got some sort of things which I won't really report yet because it's not all set in stone, but there's still some interesting open questions here. But now, instead of looking at more general kernels that might satisfy a weaker condition, now we're going to specialize to just one of our example operators. So from the second slide, we talked about the Hilbert transform, and we talked about the n-dimensional analogs of the Hilbert transform, which are the Riesz transforms. And let's just recall their formula. They have this sort of normalizing factor out front, and it's given by convolution with the jth component over the modulus to the n plus first power. Okay, so these are examples of Calderon-Zygmund operators, and as such, they satisfy the weak type inequality. And now here, I'm gonna avoid using the squiggles, and I'm gonna write a constant Cn here, because the only parameter, like we have an actually defined explicit operator, and we're working with the Lebesgue measure, so the only parameter that this could really depend on would be the value of n, so the dimension of the space we're working in. So there has to be a constant, possibly depending on n, so that this inequality holds. And we're going to call this the weak type norm. So the norm of the Riesz transform going from L1 into weak L1. The question is, what is this constant? That's an unknown question that I think people agree is kind of hard. But in particular, how does this quantity depend on the parameter n? Okay, so we're looking at this for the specific case, and we want to know, how does this depend on n? Well, if we look at the proofs that we talked about, all the proofs so far that we talked about, it's not really good because they all show that this quantity is going to grow at most exponentially in n. But if we're trying to get this down and understand what this would be exactly, we could probably do better than exponential. And that's the case. In 2004, John Ackerman proved that the weak L1 norm is going to grow at most logarithmically in n. So there's going to be some absolute constant here. Now the squiggle says it's just going to be some absolute constant. And the way that it's going to depend on n is with a logarithm. And his proof is essentially the same as the Calderon-Zygmund decomposition, except it's different because instead of working with cubes, he's working with semi-cubes, which are basically rectangles or higher dimensional rectangles where the side lengths could be one of two quantities. And instead of inflating by a large number, he inflates by some smaller quantity depending on n that allows you to double back with an absolute constant. But it's basically the Calderon-Zygmund decomposition with some more intricate estimates and two changes. So now the question is, can this logarithmic dependence be improved? There's no known lower bound for this quantity, and a lot of people think that it should be dimension free. So the question is, can we actually improve this logarithm? In particular, what do these Nasaroff-Chale-Volberg ideas say about this? So using these ideas, we can prove one reduction. And this was with Daniel Spector and myself, and this was recently, as of like a week ago, accepted to Communications in Contemporary Math. And what we can prove is the following. We're going to look at these level sets of the Riesz transform applied to F, and there's going to be an absolute constant here. So this does not depend on n. We're going to get a term with what exactly we want on the right-hand side, 1 over lambda times L1 norm of F. And then we have to study the level sets of the Riesz transform applied to these measures nu, where these nus are like these linear combinations of Dirac masses. So remember the Nasaroff-Chell-Volberg in non-homogeneous spaces basically said you can do a decomposition to reduce the estimate to a weak type estimate on linear combinations of Dirac masses. And what we can do here is actually do that reduction in a dimension-free way. So you can reduce without a dimensional penalty to the case where you're studying the Riesz transform applied to Dirac masses. And from there, if we're studying this inequality on Dirac masses, we can recover the logarithmic dependence. So basically the idea is we want to look at that Hormander condition, smoothness condition on a kernel. Instead of if you integrate on a further away space, you can get that Hormander condition to not involve the dimension. And then you're left with integrating on an annulus. And on that annulus, when you integrate that with polar coordinates, that's where this logarithmic term comes in. But anyways, with this, you have dimension-free reduction to the Dirac masses. And with the Dirac masses, you can at least regain the best known dependence of a logarithm. But the question still exists, can this, when you're looking at the linear combinations of Dirac masses, can that improve the constant with respect to the dimension n? So this is an open question that we're trying to attack. And we think that this shows promise because if you're looking at the Riesz transform applied to a function, it's kind of hard to get your hands on that. But when you're looking at the Riesz transform applied to one of these linear combinations of Dirac masses, that's going to be an explicit function. It's going to be an explicit rational function. If you look at a linear combination of these Dirac masses, and you want to apply the Riesz transform to it, it's just evaluating the kernel at the points at which the Dirac mass is located. So these masses are going to be distributed on these points Ck that are in Rn. You're just going to evaluate the kernel at that, and then take a linear combination of the kernel evaluated at these CKs. So we know what this actually is explicitly. It's a rational function. And because of that, we can study this and see what we can say. And some partial results towards this open question are, well, okay, what can we say if we have an arbitrary number of Dirac masses, but we're in dimension 1? Is that even plausible to get anything worthwhile in this case? So there's a theorem from 1946 of Loomis that says if you're in one dimension, meaning that the Riesz transform is actually just the Hilbert transform. Remember that they coincide in one dimension, and you have any number of Dirac masses in your linear combination, then you can compute these level sets explicitly. So there's an equal to sign here, and it's not a less than or equal to. There's an equal to sign. This identity says that you get 2 over pi times 1 over lambda times the total variation of your measure nu. So that's kind of promising. You can actually compute these level sets in one dimension explicitly. What we really would like to know is a higher dimensional analog of this theorem. That could kind of settle this open question. If you would know what these level sets, if you replace H by the Riesz transform in n dimensions. That's what we want to know. But in one dimension, you can actually compute that. And it does take advantage of the fact that this set here is going to be a union of a bunch of intervals. And then you can sum the measure of these intervals and get this quantity. Okay, but what about if we're an arbitrary number of dimensions? What can we say? Well, if we have just one Dirac mass, so your nu is just not a linear combination, just a weight times the Dirac mass centered at some point C, and we'll say we're in n dimensions. Then what can we say? We have a positive parameter lambda, and we look at one of these level sets. Well, this is, again, we can compute what Rj applied to nu is, which is something that we can't do for arbitrary L1 functions. But in this case, we know that that's just going to be evaluating the kernel at the point. And then we're going to use a crude upper bound on that quantity, the size estimate, essentially, of our Calderon-Zygmund kernel. And we'll get this, this expression. Then that's just going to be equal to, because we can rearrange this inequality. And really, this is just the set of x's where if we multiply the x minus c to the n over to the other side, divide by lambda, and take an nth root of both sides, this is just a ball. This is a ball centered at c of radius this gamma function over this pi to the power, absolute value of a over lambda, all to the 1 over n power. So this is a ball. And in n dimensions, balls are, we can say that it has this measure. So you multiply by the measure of the unit ball. We have our normalization factor, and we have the 1 over lambda, and we have the total variation of nu, which in this case is just going to be the absolute value of our number a. Okay, and then you can compute what the volume of the unit ball in Rn will be. So that's all that's being done here. And it's given by this expression that looks like gamma functions and pi's involving n. And then using Stirling approximations, we can get the asymptotics of this expression. It actually looks like 1 over square root of n times 1 over lambda times the total variation of nu. So in the case where we're in 1 dimension and we have any number of point masses, we can compute what the level sets are explicitly. And that was done since the 40s. Another situation when we have 1 Dirac mass and we're an arbitrary number of dimensions, we can see that this actually is going to go to 0 as n goes to infinity. So we have this decay, which is even better than what we were kind of expecting. But the question is, what happens in n dimensions when we have an arbitrary number of Dirac masses? And in that case, the geometry gets pretty complicated, and we don't have a sufficient answer yet, but something we're still thinking about. Okay, and here are all of the references. Thank you for attending and your attention.